Imagine being told over 2,000 years ago that tiny, invisible creatures could make you sick, long before microscopes even existed. Picture this: ancient thinkers suggesting that everything you see and touch is made of unimaginably small, indivisible particles, millennia before scientists could even begin to prove it. And how about this? Someone not only figured out the Earth was a sphere way back then, but also calculated its size with astonishing accuracy, using little more than shadows and clever thinking. These aren't wild guesses. These are documented ideas from people who lived centuries, even millennia, before the scientific tools and methods we rely on today. It makes you wonder just what they knew and how. Number 6. They knew fossils were ancient life forms and that the Earth changed. Way back in ancient Greece, around the 6th century BCE, a philosopher named Xenophanes of Colophon was looking at some very curious things. He found impressions of seashells and fish embedded in rocks, sometimes high up in mountains far away from any sea. Now, in his time, people had all sorts of explanations for these. Maybe they were tricks of the gods, or strange minerals that just happened to look like sea creatures. But Xenophanes had a different idea, one that was pretty radical for his era. He looked at these stony imprints and suggested that they were actual remnants of once living animals. He reasoned that if he was finding sea creatures in the mountains, it must mean that those mountains were once underwater. This wasn't just a fleeting thought. He reportedly found these fossils in places like Malta, Paros, and Syracuse. He didn't just stop at seashells. He also observed impressions of laurel leaves in rocks in Paros. His interpretation was that the Earth hadn't always been the way it was in his time. He proposed that the land and sea had changed places, that areas once submerged were now dry land, and vice versa. He even suggested that the world experienced cycles of being covered by water and then drying out, possibly wiping out human life, which would then have to re-emerge. Think about what most people believed then. Myths often spoke of a static world created by gods, or perhaps a world that had undergone a single great flood. Xenophanes was talking about vast geological times, scales and profound environmental transformations, ideas that wouldn't really take hold in mainstream science for more than 2,000 years. His contemporary, Herodotus, the famous historian, also noted seashells in the Egyptian desert, and similarly speculated that the sea had once extended much further inland. These observations were quite astute. For centuries, however, these kinds of insights were largely overshadowed. While some classical authors mentioned fossils, the prevailing views through the Middle Ages often reverted to supernatural explanations, or the idea that fossils were sports of nature, lusus naturae, peculiar mineral formations that coincidentally resembled living things, or perhaps were unfinished attempts by a creative force. Some believed they were remnants of Noah's flood, which, while acknowledging a watery past, didn't quite capture the immense timescale or the cyclical nature Xenophanes hinted at. The idea that species could become extinct was also not widely accepted. The world was often seen as having a fixed number of life forms created at the beginning. It wasn't until the Renaissance and the subsequent centuries that scholars began to systematically study fossils again with a more scientific eye. Figures like Leonardo da Vinci in the late 15th and early 16th centuries also argued correctly that fossils were the remains of ancient life, and that the positions of land and sea had changed over time. He observed shells on mountaintops and, much like Xenophanes, concluded that these areas must have once been seabeds. However, even then these ideas struggled against established dogma. The real shift came much later, in the 17th, 18th, and particularly the 19th centuries, with the birth of modern geology and paleontology. Scientists like Nicolaus Steno in the 17th century laid down principles for interpreting rock layers, stratigraphy, and firmly established that fossils were the remains of once living organisms. Later, Georges Cuvier, in the early 19th century, championed the concept of extinction, showing that many fossilized creatures no longer existed. Charles Lyell, a contemporary of Darwin, popularized the idea of uniformitarianism, the concept that the Earth was shaped by slow, continuous processes over vast periods, the very kinds of processes that would explain how mountains could rise from seabeds. These developments confirmed that the Earth had a long dynamic history and that life upon it had changed dramatically, ideas that echoed the early thoughts of Xenophanes. He didn't have the tools or the accumulated knowledge of later scientists, but his observations and his reasoning led him to a remarkably prescient understanding of Earth's deep past and the true nature of those strange stony relics. Number 5. They figured out the Earth was a sphere and even measured it. For a very long time, it was pretty common to think the Earth was flat. Kind of looks that way when you're standing on it right. A vast, flat plain stretching out to the horizon may be covered by a dome-like sky. But even in ancient Greece, some very smart people started to suspect this wasn't the whole picture. As early as the 6th century BC, the philosopher Pythagoras, famous for his theorem about right-angled triangles, is often credited with being one of the first to propose that the Earth was a sphere. Why a sphere? Well, the Greeks loved harmony and mathematical perfection, and a sphere was considered the most perfect solid shape. They also observed that the moon and sun appeared to be spheres. By the 4th century BC, this idea was gaining more traction. Plato, another hugely influential philosopher, wrote about a spherical Earth. His student, Aristotle, provided actual observational evidence to support this. Aristotle noted that travelers going south saw different stars in the sky, stars that weren't visible further north. This wouldn't happen if the Earth were flat. He also pointed to the Earth's shadow on the moon during a lunar eclipse. It was always round, no matter how the Earth turned. A flat disk would sometimes cast an oval or a line-shaped shadow, but a sphere always casts a circular shadow. These were pretty compelling arguments for the time, but knowing the Earth is a sphere is one thing. Figuring out how big that sphere is without being able to fly into space and look at it is a whole different challenge. This is where a brilliant librarian and scholar named Eratosthenes of Cyrene comes into the story. Eratosthenes lived in the 3rd century BC and was the chief librarian at the Great Library of Alexandria in Egypt, a center of learning in the ancient world. He heard about a fascinating observation in a town called Syene, modern-day Aswan, in southern Egypt, on the summer solstice, around June 21st. The midday sun was directly overhead. This meant that vertical objects, like a well, cast no shadow, and the sun's rays shone straight down to the bottom of deep wells. Eratosthenes realized he could use this fact to measure the Earth's circumference. He knew that on the same day at the same time in Alexandria, which he believed was roughly due north of Syene, vertical objects did cast a shadow. He measured the angle of the sun's rays in Alexandria at noon on the summer solstice and found it to be about 7.2 degrees, or about 1/50th of a full circle, 360 degrees. He reasoned that this difference in angle was due to the curvature of the Earth. If he knew the distance between Syene and Alexandria, he could calculate the Earth's total circumference. The distance was estimated by professional walkers, called bimetists, who were trained to walk in even paces. It was said to be about 5,000 stadia. The stadion was an ancient unit of length, but its exact measure varied. Depending on which stadion Eratosthenes used, it's thought to be the Attic stadion of about 185 meters. His calculation for the Earth's circumference came out to be remarkably close to the actual value we know today, around 40,000 kilometers or 24,900 miles. His estimate was somewhere between 39,375 and 46,620 kilometers. Even if he was off by a bit, the very fact that he conceived of this method and carried it out with the tools available was an incredible intellectual feat. For many centuries, this knowledge of a spherical Earth, and even its approximate size, was preserved by scholars, though not always widely understood by the general populace. During the Middle Ages in Europe, while some educated individuals retained classical knowledge, simpler, flatter Earth models sometimes resurfaced in popular imagination. However, scholars and navigators, especially by the later medieval period, were generally aware of the Earth's sphericity. By the time Christopher Columbus set sail in 1492, the debate among the learned wasn't whether the Earth was round, but rather how large it was and how far west one would have to sail to reach the East Indies. Columbus, in fact, used a smaller estimate for the Earth's circumference, which made him believe Asia was closer than it actually was. Had he known Eratosthenes' more accurate figure, he might have been less confident about his voyage. The later voyages of Ferdinand Magellan in the early 16th century, which successfully circumnavigated the globe, provided definitive practical proof of what ancient Greek thinkers had deduced through observation and reason over 1,700 years earlier. The eventual images of Earth from space in the 20th century gave everyone the visual confirmation that those ancient minds had, in a way, already seen with their intellect. Number 4. They suggested tiny invisible creatures caused diseases. Imagine living in a world where diseases swept through populations and nobody truly understood why. Common explanations often involve divine anger, bad air, miasma, or imbalances in the body's humors. The idea that something tiny, something you couldn't even see, could be the culprit was a massive leap in thinking. Yet, remarkably, this very idea was floated by a few encyclical individuals long before the invention of the microscope. One such person was Marcus Terentius Varro, a Roman scholar and writer who lived in the 1st century BCE. In his work on agriculture, Rerum Rusticarum Libri Tres, 3 books on agriculture, Varro offered some surprisingly modern-sounding advice about where to build a farmhouse, cautioned against building near swamps, not just because they were damp and unpleasant, but for a more specific reason, he wrote, and because there are bred certain minute creatures that cannot be seen by the eyes, which float in the air and enter the body through the mouth and nose, and there cause serious diseases. Minute creatures invisible to the naked eye, causing disease. That's an astonishingly accurate description of what we now know as germs or microbes. He didn't have any way to prove this, of course. There were no microscopes to see these minute creatures. It was a hypothesis based on observation and reasoning. People who lived near swamps often got sick with fevers, likely malaria, which we now know is spread by mosquitoes breeding in swamps, carrying Plasmodium parasites, still tiny creatures causing disease. Varro wasn't entirely alone in thinking along these lines, even if his statement is one of the most explicit. Across the world in ancient India, similar ideas were emerging. The Sasrota Samhita, an ancient Sanskrit text on medicine and surgery, attributed to the physician Susruta, with its origins possibly dating back to around 600 BC, though compiled over centuries, also contains passages that hint at the spread of disease through unseen agents. While it doesn't use the exact invisible creatures phrasing as explicitly as Varro, it discusses the importance of hygiene, clean water, and how certain diseases could be communicable. It describes how diseases like leprosy, fever, consumption, and eye diseases could be transmitted from one person to another through close physical contact, sharing utensils or beds, or even through breath and shared air. This implied some sort of transmissible agent. Even if its nature wasn't fully understood, The text emphasized meticulous cleanliness during surgical procedures, including sterilization of instruments by heating, which would indeed kill microbes, suggesting an empirical understanding that cleanliness prevented post-operative infection. For the vast majority of human history that followed, these early insights into contagion and invisible disease causers were largely lost or ignored in many parts of the world. The miasma theory, the idea that diseases were caused by bad air emanating from decaying organic matter, became the dominant explanation in Europe for centuries, right up through the 19th century. While this theory did sometimes lead to beneficial public health measures like swamp drainage and improved sanitation, because these reduced bad smells, it didn't grasp the true nature of infection. The concept of specific living agents causing specific diseases was not the prevailing view. It took until the latter half of the 19th century, with the groundbreaking work of scientists like Louis Pasteur and Robert Koch, for the germ theory of disease to be firmly established. Pasteur's experiments showed that microorganisms were responsible for fermentation in disease, and that they didn't arise spontaneously but came from other microorganisms. Koch developed methods for isolating and identifying specific bacteria responsible for diseases like anthrax, tuberculosis, and cholera. The invention and improvement of the microscope were absolutely crucial to these discoveries, allowing scientists to finally see the minute creatures that Varro had hypothesized nearly 2,000 years earlier. Principles of hygiene, sterilization, and understanding of communicable diseases that followed revolutionized medicine and public health, dramatically increasing human lifespan. It's quite something to think that the core idea in a nascent form was voiced by a Roman farmer scholar and hinted at by Indian surgeons so very long ago. Number 3. They had ideas about life changing over time, kind of like evolution. Long before Charles Darwin published On the Origin of Species in 1859 and laid out the theory of evolution by natural selection, some ancient thinkers were already mulling over the idea that life wasn't static and that species, including humans, might have changed over vast stretches of time. These weren't fully formed theories of evolution as we understand them today, lacking the mechanism of natural selection. But they were challenging the then common beliefs in a fixed, unchanging natural world created perfectly from the start. One of the earliest known figures to propose such ideas was Anaximander of Miletus, a Greek philosopher who lived around the 6th century BCE. He's a bit of a shadowy figure, as most of his writings are lost, but later commentators described his intriguing theories about the origins of life. Anaximander believed that life first arose in water, in the moist element, when it was acted upon by the heat of the sun. He suggested that the first animals were fish-like creatures, covered in prickly or scaly skin. What's particularly striking is his idea about human origins. He proposed that humans must have originated from creatures of a different kind, specifically from these fish-like beings. His reasoning was that human infants are helpless for a long time and require extended parental care. If humans had first appeared on Earth in their current form, they wouldn't have been able to survive. Therefore, he argued, they must have developed inside these aquatic creatures much like a fetus, and were only released onto land when they were capable of fending for themselves. This is a fascinating early stab at explaining how complex life forms like humans could have come into being from simpler origins, and it clearly points to an aquatic ancestry. A century or so later, another Greek philosopher, Empedocles of Acragas, 5th century BC, offered a different and rather bizarre but still evolutionary flavored vision of how life formed. Empedocles believed the universe was made of 4 fundamental elements: earth, air, fire, and water, acted upon by 2 forces: love, attraction, and strife, repulsion. He imagined a period when love was gaining dominance, and individual body parts, arms, legs, eyes, heads, spontaneously formed from the earth and roamed around separately. As love brought things together, these isolated limbs and organs would combine randomly. Many of these combinations would have been monstrous and non-viable. Heads with no necks, arms without shoulders, human heads on ox bodies. Empedocles suggested that only the combinations that happened to be well adapted and functional, those fitted for survival, managed to live, reproduce, and persist. The ill-suited, monstrous forms simply perished. While the mechanism of randomly assembling body parts is fantastical, the core idea that forms better suited to their environment survive and reproduce, while unfit forms die out, has a distinct flavor of natural selection, or at least a survival of the fittest concept. The Roman poet and philosopher Lucretius, in the 1st century BC, expanded on similar ideas in his epic poem De Rerum Natura, on the nature of things, which drew heavily from the Greek atomist, philosophers like Epicurus, who himself followed Democritus. Lucretius also described a primitive earth that spontaneously produced various forms of life. He wrote about how the earth first put forth grasses and trees, then birds, then land animals. Like Empedocles, he imagined many monstrous and unviable creatures being formed initially, which could not feed themselves or reproduce, and thus died out. Only those creatures that possessed qualities like strength, speed, cunning, or those that became useful to humans, like dogs or sheep, through a kind of early domestication idea, were able to survive and propagate their kind. He explicitly rejected the idea that gods designed animals, attributing their forms and abilities to these trial and error processes over time. He also speculated that early humans were hardy, lived in caves, and gradually developed tools, language, and society. These ancient ideas about life changing, about monstrous forms perishing while fitter forms survived, and about humans originating from simpler, perhaps aquatic life forms, were largely submerged for centuries. The rise of creationist narratives, which posited a divine and perfect creation of all species in their current forms, became the dominant worldview in many cultures. While naturalists observed variations within species, the overarching concept of common descent and transmutation of species remained outside mainstream thought. It wasn't until the 18th and early 19th centuries that scientists like Jean-Baptiste Lamarck began to seriously propose theories of species change over time, though Lamarck's proposed mechanism, the inheritance of acquired characteristics, was later disproven. Finally, in 1859, Charles Darwin and Alfred Russel Wallace independently proposed the theory of evolution by natural selection, providing a robust, testable mechanism for how life diversifies and adapts. Darwin, in The Descent of Man, specifically addressed human evolution from ape-like ancestors, which itself echoed, in a much more scientifically grounded way, Anaximander's ancient intuition about humans developing from different earlier forms. The fossil record, genetics, and comparative anatomy would later provide overwhelming evidence supporting the theory of evolution, confirming the deep connections between all living things and the immense history of life's transformation on Earth. A transformation that a few bold thinkers in antiquity had dared to imagine. Number 2. One guy said the sun was the center, not the Earth. Ages ago. For most of human history, it just seemed obvious. The Earth stood still, and everything in the sky, the sun, moon, planets, and stars, revolved around us. This geocentric, Earth-centered view was the common sense model, and it was formalized by influential thinkers like Aristotle, and later in the 2nd century CE by Ptolemy, whose Almagest became the definitive astronomical text for over 1,400 years. Ptolemy's system, with its complex arrangement of circles upon circles, epicycles, and deferents, was remarkably good at predicting the positions of planets, which further solidified its acceptance. So imagine the audacity of suggesting the opposite, that our seemingly solid, unmoving Earth was actually hurtling through space, spinning on its axis, and revolving around the sun. Yet, This very idea, the heliocentric, sun-centered model, was proposed by a Greek astronomer and mathematician named Aristarchus of Samos, way back in the 3rd century BCE, nearly 1,800 years before Copernicus. Most of Aristarchus's original writings are lost, but his heliocentric theory is described by other ancient authors, most notably Archimedes, the famous mathematician and inventor. In his work, The Sand Reckoner, Archimedes mentions that Aristarchus had published a book or hypotheses in which he proposed that the fixed stars and the sun remain unmoved, that the Earth revolves around the sun in the circumference of a circle, with the sun lying in the middle of the orbit, and that the sphere of the fixed stars is immensely vast. What led Aristarchus to such a radical conclusion, so contrary to everyday experience and prevailing wisdom? We don't know his full reasoning, but we do know he was a brilliant mathematician and observer. His only surviving work is on the sizes and distances of the sun and moon. In this treatise, he attempted to calculate the relative sizes of the sun, moon, and earth, and their distances from each other, using ingenious geometric methods based on observations of lunar eclipses and the angle between the sun and moon at half moon. While his measurements weren't perfectly accurate due to the difficulty of precise observation without sophisticated instruments, his calculations led him to conclude that the sun was much, much larger than the Earth, perhaps 6 to 7 times the Earth's diameter. Modern figures show it's about 109 times. It's highly likely that this realization of the sun's immense size compared to the Earth played a key role in his heliocentric thinking. It might have seemed more logical to him that the smaller body, Earth, would orbit the much larger body, Sun, rather than the other way around. Aristarchus's heliocentric model also included the idea that the Earth rotates on its own axis once a day, which would explain the daily rising and setting of the sun and stars. This was another departure from the common view of a stationary Earth. However, his theory was not widely accepted in antiquity. There were several reasons for this. Firstly, it contradicted the dominant physics of Aristotle, which held that earthy objects naturally move towards the center of the universe, which was assumed to be the Earth itself. Secondly, if the Earth were moving through space, people expected to feel a strong wind or see objects left behind. Thirdly, and perhaps most scientifically, if the Earth orbited the Sun, astronomers expected to see an effect called stellar parallax, an apparent shift in the position of nearby stars relative to distant stars as the Earth moved from one side of its orbit to the other. No such parallax was observed by ancient astronomers with their naked eye instruments. Aristarchus himself reportedly addressed this by proposing that the stars were incredibly far away, so far that the parallax would be too small to detect. This too was a visionary idea, suggesting a universe far vaster than most people imagined. Despite the support of at least one other ancient astronomer, Seleucus of Seleucia, 2nd century BC, who reportedly proved the heliocentric system, though his methods are unknown, Aristarchus's model was largely forgotten or dismissed in the Western world for centuries. Ptolemy's geocentric system, with its mathematical sophistication and ability to predict planetary motions with reasonable accuracy, reigned supreme. It wasn't until the 16th century CE that the heliocentric idea was revived and presented in a comprehensive, mathematically rigorous form by the Polish astronomer Nicolaus Copernicus in his landmark book, De Revolution of the Celestial Spheres, published in 1543, the year of his death. Copernicus himself was aware of Aristarchus's ancient proposal and mentioned him in an early draft of his book, though the reference was removed before final publication. Copernicus's work, initially met with resistance, kick-started the scientific revolution. Later astronomers like Johannes Kepler, who described planetary orbits, Galileo Galilei, whose telescopic observations like the moons of Jupiter and phases of Venus provided strong evidence against a Ptolemaic system, and support for heliocentrism, and Isaac Newton, whose laws of motion and universal graph to summon year court for heliocentrism of Y planets. The stellar parallax that ancient astronomers couldn't detect was finally measured in the 1830s by Friedrich Bessel, confirming Aristarchus's intuition that the stars were indeed immensely distant. It took nearly 2 millennia for the world to catch up to a brilliant insight from a lone astronomer in ancient Samos. Number 1. They dreamed up atoms, the building blocks of everything. Think about everything around you. Your phone, the air you breathe, your own body. What if all of it, in its incredible diversity, was made up of unimaginably tiny fundamental particles that couldn't be divided any further? This idea, that matter is composed of discrete, indivisible units called atoms, is a cornerstone of modern science. Concept didn't begin with lab coats and particle accelerators. It started in the minds of philosophers more than 2,000 years ago, in both ancient Greece and ancient India. In Greece, around the 5th century BCE, the philosopher Leucippus and his more famous student, Democritus of Abdera, are credited with developing the theory of atomism. Democritus, often known as the laughing philosopher, proposed that the entire universe was composed of two fundamental things: atomos, which means uncuttable or indivisible in Greek, and the void or empty space in which these atoms move. He believed that atoms were infinite in number and came in an infinite variety of shapes and sizes. They were all made of the same fundamental substance, but differed in their form, arrangement, and position. These atoms were constantly in motion, colliding, and either bouncing off each other or hooking together due to their shapes. Some might have had hooks and barbs, others might be smooth spheres, to form the objects we see and experience in the world. Everything from rocks and water to plants and animals, and even the human soul, was thought to be composed of these atoms. Differences in substances were due to the differences in the types and arrangements of their constituent atoms. For example, water might be made of smooth, round atoms that could flow easily, while iron might be made of jagged atoms that locked together tightly. This was a purely philosophical and speculative idea. They had no experimental means to verify it. It was an attempt to explain the nature of reality and change through reason. Around a similar period, or perhaps a bit earlier or later, chronology is debated, possibly between the 6th and 2nd centuries BCE. A parallel concept of atomism arose in India with the Vaisheshika school of philosophy, founded by the sage Kanada. Kanada, whose name is sometimes said to mean atom eater, also proposed that all material things were composed of tiny, indivisible particles called anu or paramanu, the smallest ultimate particle. These atoms were considered eternal and possessed different qualities, like smell, taste, color, touch, that corresponded to the elements they formed, such as earth, water, fire, and air. Unlike the Greek atoms that combined due to shape, Kanada's atoms were thought to combine in specific ways to form dyads, divinuka, 2 atoms, and triads, trianuka, 3 dyads, which then aggregated to form larger objects. The Vaisheshika system was incredibly detailed in its classification of matter and its properties based on these atomic combinations. Like its Greek counterpart, Indian atomism was a philosophical endeavor to understand the ultimate nature of physical reality. These ancient atomic theories were remarkable for their time, offering a mechanistic explanation for the universe without resorting to constant divine intervention for every phenomenon. However, they faced significant opposition. In Greece, influential philosophers like Plato and Aristotle were critical of atomism. Aristotle, in particular, favored the theory of the 4 elements: earth, air, fire, water, that were continuous and infinitely divisible, not particulate. Since Aristotle's philosophy became profoundly dominant in Western thought for many centuries, atomism was largely sidelined, though never entirely forgotten. Roman poets like Lucretius, in his De Rerum Natura, beautifully articulated Epicurean atomism, which followed Democritus, keeping the idea alive. In India, atomistic ideas continue to be debated and developed within various philosophical schools. For over 2 millennia, atomism remained largely a philosophical curiosity rather than a scientific theory. The concept of indivisible particles was hard to reconcile with the observed continuity of matter. It wasn't until the early 19th century that the English chemist and physicist John Dalton revived the atomic theory on a scientific basis. Dalton's atomic theory, based on experimental observations of chemical reactions, particularly the law of definite proportions and the law of multiple proportions, proposed that elements are composed of atoms, that atoms of a given element are identical in mass and properties, and that chemical compounds are formed when atoms of different elements combine in simple whole number ratios. This was a pivotal moment, transforming atomism from speculation into a powerful, explanatory framework for chemistry. Later discoveries in the late 19th and early 20th centuries, such as J.J. Thomson's discovery of the electron, Ernest Rutherford's discovery of the atomic nucleus, and Niels Bohr's model of the atom, revealed that the atom itself was not indivisible after all, but had an internal structure. The development of quantum mechanics further revolutionized our understanding of the subatomic world. Yet, the fundamental concept that matter is particulate at a very small scale, an idea first articulated by Democritus, Leucippus, and Canada, remains. While modern atoms are known to be divisible into even smaller particles, protons, neutrons, quarks, the ancient leap of imagination to conceive of fundamental, discrete building blocks of the universe, at a time when there was no empirical evidence to support it, stands as an extraordinary testament to the power of human thought to probe the nature of reality.